Hey guys, hopefully you're doing better with all this these area problems, and the explanations are making it clear as to what we're doing for each of them. So let's move on to a new type of area 1, or it's just an adjustment to it. I guess it's really not a new type, it's just kind of changing the way we think about these. So if we're looking at this one, right, and we have y equals the square root of x and y equals x minus 2, and we're also bounded by the x-axis. So if we're looking at that right here, right, that would be, here's the x-axis, here's the one, that's the y equals x minus 2, and then here's the square root of x. You can see that for this one here, there's a little different way to think about it, because if we make our rectangles here, right, our rectangles, if we made them up and down here, they're going to have the top bound, the top of the rectangle, right, because remember this thickness is the change in x and the height here is the change in y. The change in y here is going to be between the square root of x and the x-axis until it gets to right here. Okay, once it gets here, now the lower bound is determined by this line in blue. Okay, so because of that, because it's changing which function is the lower bound, you're going to have to set up for this one two integrals if you're going to choose to do it right with the slices, the slivers, the rectangles are going to have a width of dx, like for yourself. Okay, and so it's going to go from 0 to 2, right? 0 to 2, and from 0 to 2, we're going to use our upper bound as the square root of x, and our lower bound is just the x-axis. So I don't need to write minus 0 there. Right? I can just integrate it as is. Okay, so that's for this, right? That's going to give you this. If we want to get this area here in pink for ourselves, right? You can see that we have our rectangle, right, for ourselves is going to have a different top. It's going to have the same top but a different bottom. Okay, so this one's going to apply. This region is going from 2 to 4, with the upper bound being the square root of x again, but this time the lower bound is going to be the quantity x minus 2 for ourselves. So we're going to have those two regions. Okay, so we'd have to integrate these two completely separately. We do that integration, and then boom, we get our answer. Okay, so another way to think about this one, though, right? This is one way to do it, right? Let's say you don't want to have two integrals for this. Okay, and so I'm going to go back and I'm going to do a quick sketch of this. I already made that other one messy. Okay, there's my region again. Okay, now if I were to choose instead to make my rectangles go from left to right here, then I would have the same bound as the same function as the upper limit and the same function as the lower limit, right? The entire way from here to here. This would always be the larger, and this is always the smaller. Because as we look at it, how do we know which one's larger and smaller? Remember, if you're looking at, in this case, this is the height of the rectangle. The height of the rectangle is the larger x minus the smaller x. Okay, so want to think of it like that. Remember, we talked about that before. It's the larger minus the smaller. In this case, the thickness of the rectangle there is dy. It's infinitely thin. Right? Remember that we've been talking a lot about these, to find these area of the regions. You're adding up all these rectangles. Rectangles have an area of base times height. Right here, our height is infinitely small. It's dy, and our width here is the change in x's, the larger minus the smaller. Okay, so if we do that, we just need to think of these equations and basically change them around here, right? And so it's going to be x equals y cubed, and this equation here, which was y equals x squared, we're going to make it x equals y plus 2. Now the reason we have to change it to y is because, remember, this rectangle has a thickness of dy, and that tells us that this expression here has to be in terms of y. So whatever your thickness of the rectangle is, right, that infinitely small thickness, that tells you what variable you're going to have. So in this case, we're going to have y plus 2, right, minus y squared, right, the upper minus the lower, right, and that's how tall each rectangle is going to be, and that is the thickness of each rectangle. Okay, because we're integrating in terms of y, we have to think about what y varies from. We're not going to pick 0 to 4. That's what x varies between. What is y varying between? Well, the minimum value for y is 0 right here. The maximum is 2 when it hits that intersection. So our bounds are going to be 0 to 2. Notice if I set it up this way, I only need one integral for myself. I don't have to do two pieces. Okay, so there's less thinking in the sense of, oh, how, or less integration. Right? There's a little bit more thinking here because you have to kind of change the way we're thinking about it and integrate in terms of y for ourselves. Okay, so either way we integrate, I'm just going to show you that these are going to be the same. So if I integrate this one, it's going to be y squared plus 2y minus y cubed over 3. And that's the bounds for that are 2 to 0. Love that 0 is a lower bound. It's just going to go away. The upper bound we have 4 plus 4 minus 8/3. Okay. And so that's going to give me 8 or 24/3. So that's overall 16/3. Right. If I do this one, I should get the same answer. If I do the antiderivative of this, I'll have two pieces. Right. So again, this is a little bit annoying. Right. 2/3. And that's integrating from 2 to 0. And then this one is going to be 2/3 x to the 3/2 minus x squared over 2 plus 2x. Remember, I distribute that negative in there, so okay, that's why I got that. And then I have to evaluate from 4 to 2. Okay, so in this, if you look at this, this is going to be a ton more work. Right, you're wasting a lot of time that you could just avoid by making it go side to side, your rectangles instead of up and down. Okay, so please don't get stuck in the mindset that the rectangles must go up and down. You want to do what's easiest for the problem. Sometimes you don't have a choice, and the problem's going to tell you what to do. All right, but you can see, like, look at this, man. This was so quick and easy. Up here, not quick and easy. I guess I'll keep going, even though I really don't want to, because it's going to be so annoying and obnoxious, these numbers, as I do them. Oh man. Look at that, 2 to the 3/2, right? And then we got this, and no, I'm done. I'm not doing it because it's just going to get so messy, and it's wasting my time because I have that. Okay, if you integrated it, yes, you'd get 16/3. I don't want to do it. It's not worth my time. Okay, so let's take a look at the second one here. You can see I'm kind of ignoring what it says strategy 1, strategy 2 here. All right, I'm just going to do everything. All right, here's strategy 1. Strategy number 1 is use dx and create two integrals. Right, strategy 2. Use dy. Just why? I mean, even writing it out as to what we're doing there, right, is easy. Sorry, that was a little bit high there. All right, so use dx and create two integrals. Strategy 2, use dy. Okay, so okay, and guys, remember, if you need to pause it and rewatch any piece, right, do that, right, to help you understand it if I went through something too quickly. Okay, this is the same. This is exactly what we just did. So that's what we just did. You can see that they just changed it. So let's go and try some more problems like that.